So just a reminder, this talk is being live streamed, so if you'd like to catch Glenn and Rafe's excellent talk on audio performance, you can go to that one and then watch ours at the same time. Last year, we gave a talk where we introduced Android Jelly Bean 4.1, and 4.2 came out soon after that. And today, we would like to announce
graphics and performance. The joke would have worked a lot better, but for some reason, for the live stream, we have to show the title slide first, so we had to go back. Hi, I'm Romain and this is Chet Haase. We both work on the Android framework team, and we focus on graphics, performance, and animations. So this talk is divided into 3 sections. First, we're going to talk about architecture, and I'll get back to this. Then we'll talk about tools, and finally, we'll give you some tips and tricks on how to improve performance in your applications. The architecture section is interesting because for the first time, I think, ever, we're going to talk about stuff that doesn't exist yet. We're going to talk about stuff that's coming. So we can't tell you.
It's a really good way for us to not be here next year to give any talk to you on behalf of Google,
yeah.
But we're going to try it anyway.
That doesn't mean it's going to come out next year or this year. We can tell you when, we can tell you how, we can tell you what version number, what name. It's just coming sometimes in the future.
Maybe.
Hopefully.
So first of all, one of the architectural changes that we have implemented in this fictional future release is reordering and merging. If you recall last year, if you happen to be in a session called For Better or Worse, we gave a really confusing diagram of what's actually going on in the rendering engine, and it bottoms out in something that we call display lists, which is basically our intermediate mode of the commands that we're going to send down to the GPU. Then we compose OpenGL commands out of that and then send them on down, and they get rendered, hardware acceleration, life is good. What we have done recently is implemented some changes so that we can actually reorder and merge commands to make it more optimal the way that we actually talk to the GPU. We have in previous talks and in articles recommended a tip where you should batch your commands. So if you're doing a bunch of, like, I'm going to draw a bitmap, I'm going to draw some text, I'm going to draw a bitmap, draw some text, it's actually much better for us and for the GPU if you draw all the bitmaps at once and all the text at once. And that's a good approach that you can still take. But what we've done is try to remove that from you and just do it more automatically. And in fact, it turns out that we can actually do even better than that.
Yeah, so for once, we're making your life easier instead of harder.
I don't know how that happened.
And there's not even an API. It's all automatic.
So let's pretend that this is a sample UI, a very boring sample UI, but a sample UI nonetheless. We have a couple of checkboxes, each one with some text. We have a couple of buttons. Let's pretend that the order that we see it on the screen is the order in which they're added to the containers there. So we're basically going to draw it in this order. So we're going to, there's the order. We're going to draw the checkboxes. So we draw a bitmap with the checked checkbox, and then we're going to draw.
I'm going too quickly.
Oh, that animation was so awesome, we're going to do it again.
All right.
We're going to draw a bitmap, we're going to draw some text, we're going to draw a bitmap, draw some text, we're going to draw a 9 patch, draw some text, a 9 patch, and draw some text. 8 commands, not a lot to worry about, but let's see what happens when we actually are able to reorder these things. So we can switch things around so that before we send it down to the GPU in the display list itself, we switch the order of the command so we can actually do draw bitmap twice, draw 2 9 patches, and then draw the text that are next to and on top of those objects. That ends up being a lot faster for the GPU to process because it doesn't have to change state. Right? It's not constantly changing the state of the shaders that it's using, the state that we draw bitmaps with versus the state of text. Like, none of those things have to change, and the GPU is really happy when you don't change state. So this is a good step to begin with, and this is where you could get to if you manually batched your stuff according to when you know you're drawing stuff. We can do that for you now in this fictional upcoming release. But on top of that, we could do something that we call merging, which is we can actually take all of those commands that we have now reordered and say, you know what if we just did one command that drew 2 bitmaps in a row, and then did one command that drew 2 9 patches in a row, and then draw all the text all at the same time. Even though they're actually on different views on the screen, that's irrelevant to the GPU. All it's doing is drawing pixels on the screen. Right? So if we can do that, we've reduced essentially 8 commands to the GPU, which were originally changing state and interleaving it the entire time, into 3 commands, which is much better for the GPU and much better for performance in general.
So we have a demo. We're going to use Google Plus as an example, and I'm going to switch to one of our debugging tools. So I'm going to show you what happens when, without the reordering and the merging. So I'm going to launch that tool. It's an OpenGL debugging tool. I'm going to capture a frame, so we're going to see exactly what the app draws. And are we getting everything? Yes. So you don't have to look at in details, but as you can see, so this is the G+ UI, so you have all your cards in your stream of posts. And you can see that we draw the cards one by one because that's how they're defined in the view hierarchy. So we're going to draw those white backgrounds first, then we're going to draw the Chet's face, then we're going to draw the text, and then we'll go to the next card, and we do that over and over again. So in total here we have 88 drawing commands that have been executed on this frame. And as you can see, there's a lot of, Chet was talking about state changes, and you can see it happening here. So here we draw a bunch of text, then we switch to bitmaps, then we draw text again, then bitmaps again, then text, then bitmap, and so on and so forth. So now, if we go re-enable the new optimizations, I have to kill the app first. Of course, it has reloaded the posts, so now they're different.
Tension is building.
All right.
What's it going to look like?
And if the tool works, what makes me happy is that we have NVIDIA people at the conference this week, so if the tool insists on not working, you can go yell at them.
Is there a perf HUD doctor in the house?
So this is the workflow that we do every day, and every day it's the same. We have to try again and again and again until it works. So whenever you complain about the dev tools, just know that we're in the same boat. All right. So we went from 88 drawing commands to 39. So it's not exactly the same configuration, but you can see what's going on here. Things are drawn out of order. You can see that the text appeared in pretty much one block. We're going to go back to that. Let's go here at the beginning. So you can see that we're drawing the white backgrounds of the cards together, and then we go back to fill the inside of the cards. And then when we draw the text, there's this one spot where we draw a huge batch of text right here. And you can see the geometry here. You can see that we draw pretty much the entire text on screen in one draw call instead of many. So this is what it does for you. You don't have to worry about it. Don't change your app. It's going to be faster and better automatically. And in this future version of Android that may or may not exist, and that you may or may not get on your device, we are also going to introduce a little bit of multi-threading to the rendering pipeline. So we're still going to do the rendering on the main thread, so it's still very important that you do not block the main thread to get smooth animations. However, some of the operations that the renderer performs on your behalf will now happen on multiple cores if you have multiple cores.
Which is more and more common. The way that manufacturers are scaling performance in general tends to be going wide. So you've got, as opposed to faster and faster CPUs, which was a model for years, now we're getting multiple cores, 2 cores, 4 cores. Well, if you've got these multiple cores down there, can you take advantage of parallel processing instead of just continuing to do everything as fast as you can on one?
So here in blue, we have the main thread executing the drawing commands, so we're doing all the drawing. But if you're using drop shadows in your application, for instance, you have drop shadows on text. That's what the launcher does a lot on Android. We're going to use RenderScript, and we're going to spin up on a 4-core device. We're going to use 4 threads to generate the drop shadows. So we're going to use all the cores that we have at our disposal. And if you draw paths, so if you draw circles or arbitrary geometric shapes with curves, we're also going to use multiple cores to generate those paths in the background as OpenGL textures, so then we can draw them on the UI thread. So once again, you don't have anything to do. This is all under the hood, but just be aware of what's going on. We're also adding support for non-rectangular clipping. So this is part of the Canvas API. It wasn't supported with the hardware accelerated pipeline. So non-rectangular clipping can be used to draw very useful things, such as text in the shape of a heart. If you ever do that in your app, like I don't want to know what your app does, but it can also be used, and we'll talk a bit more about it. We will talk a bit more about that later. It can also be used to clip when you're doing rotations. So let's say you have a list view or a scroll view, and you apply a 3D rotation, so you want to flip it over. If you're not using a layer and you run that animation on existing versions of Android, like 4.1 or 4.2, you'll see that the clipping breaks, because the clip rect of the list, as you rotate it in 3D, turns into something that's not a rectangle anymore. And we didn't know how to deal with that before. But now that's fixed. or it will be fixed. And if you're curious on how to do a non-rectangular clipping and you want to clip your text with a heart, this is how you do it. So you get a canvas you can call clip path. There are other methods that you can use, like clip rect, detect parameters, so you can do those fancy shapes. And then you just draw your content, and we'll do the right thing for you.
Now, a discussion about some of the tools that we use. Some of these exist now, but we'll be talking about some slight modifications and improvements going forward and possible in fictional releases.
So the first one was introduced in 4.2, I think. It's a debug tool that's on the device. So you go to Settings, Developer Options. There's a checkbox called Show GPU Overdraw. So I wrote about it online. I wrote an article about that. How many of you know about this option or have used this option? Why are we here? You're making my job useless. So Show GPU Overdraw will colorize the screen. It will use several different colors to show you how many times you draw each individual pixel on screen. So here you have a picture of the Google Play Store with that option turned on. And you can see there's this bluish tint in the background that doesn't come from the app. That's the tool adding this blue color on the background. You can see there's a lot of red in the middle, that app called 1-800-Flowers. It's in red because we have touched a lot of pixels here. So the color code is very simple. Blue means that you've drawn, there's a 1x overdraw. So that means that you've drawn that pixel once, and then you've drawn on top of it. So there's a 1x overdraw. Green, that means that you have a 2x overdraw, so you've drawn that pixel 3 times. There's a slight difference between the two reds. It doesn't really matter, because if it's red, like you're doing something wrong. So red is 3x or 4x or more.
And if it's 5x, we just reboot the machine.
I wish I could do that.
So there is a 0x. If you actually have no redraw, which is really the goal here, then you'll just see the natural color that they're painting on the screen.
Yeah, and we'll see a demo of the overdraw and how it works and how the kind of techniques you can use to fix overdraw in a few minutes.
So this is a tool that we introduced in 4.1
last year
to track your frame rate. It seemed to be a little bit sort of inconsistent in how you would get the frame rate and how to understand how fast you were running, and more importantly, how consistently fast you were running, what your effective frame rate was in your application. So we instrumented the system to give you this information, and if you did a ADB shell commands dump sys gfx info, then we would spit out the information for the last 120 frames, and then you could take that data and you could paste it into a spreadsheet, and then you could create a shard, and apparently that was too tedious for people. So we have made that a little bit easier. So actually, if you go back to the previous slide quickly, so this gives you the information about the time that we're spending actually creating the drawing commands that are going to be issued, and then issuing the drawing commands, and then waiting for OpenGL to come back because it processed the drawing commands and swapped the buffers. So this gives you an indication of those relative times, as well as how many times that's happening per second, or what your frame rate is. So we have the same exact tool available now, but instead of making you go through the incredibly tedious and overbearing process of creating a spreadsheet to see a graph, we actually just create the graph for you on the screen. So you can pull up developer settings. You can select an option in this dialog box to see how you actually want to display this information, whether you want to use the tedious method or some on-screen graphical method instead, and you can see the results in real time, such as is demonstrated here. So we're running a calendar application. And we can see as the calendar application, I think you were probably, scrolling back and forth in the calendar application. And you can see in real time us update an overlay on the device, so you can see what the rendering performance and frame rate is like. So you'll actually see this for all active activities on the screen, which is why there's actually 3 separate charts that you'll see. You'll see one for calendar. You'll also see one for the navigation bar and the notification bar at the top.
It works in every application. And you can see it working here, right here on the device in real time. There's a green line that wasn't shown in the graph that we used last year as a demonstration. So the green line is the 16 milliseconds threshold. So if all your vertical bars are under that line, then you're going to run at 60 FPS. And if you cross that line, then there's going to be jank. I mean, it's a little more complicated than that, but basically, if you can stay below the line, you're probably in good shape in your application.
The general tip is smaller is better. Try to stay away from the green line on the underside of it. And what you will see, and also be aware of situations where you're tripping very occasionally over that green line, because then basically you drop down to half the frame rate immediately. And the net effect on the screen is that the user's going to see a stuttery animation where it was smooth and 60 FPS, and then you skipped a frame in the middle. And it's a very discontinuous and disturbing artifact.
I have to say, most of the times when you guys send us emails or ask questions, you're pretty mad at us. It's pretty cool when you're happy. I like that. Keep doing it.
Maybe that was an angry clap.
Maybe it was an angry clap. Yeah, I'm a little worried now.
Future
clap. Next, we want to talk about systrace. So systrace is this awesome tool, and you can thank Jamie right here for that tool.
Thank you, Jamie.
It's a great profiling tool that we've introduced last year. It was a little difficult to use, just like that profiling graph we showed you. It was a little bit involved to set it up. And this future version of Android, sorry, future update of Android, it's not necessarily a version number. It's easier to use systrace. So now the way you invoke systrace is still from the command line, but before you had to go to the developer options, you had to turn on several tags, like you had to tell us, I want to profile graphics, I want to profile views, I want to profile the window manager. Then you had to restart the runtime on the device, effectively rebooting the device, and then you could run your command. Now the way you do it, you just invoke the script, you specify the tags that you want to trace. So here we're tracing GFX, that's all the graphics information, view, that's all the UI toolkit information, things like inflation, layout, measure. Frec is the frequency of the different CPUs, and sched is the scheduler, so that way you can see who's scheduled on what CPU and when. And I'm going to show you an example of that. We've also added in 4.2 the ability to trace OpenGL commands. So if you use OpenGL in your application, or if you write a normal application and you're curious about how many GL commands we execute on your behalf, you can go turn that on in the developer options, and we're going to trace every individual OpenGL command, and you're going to see them in systrace. Actually, let's go with the slides for a little while. We're also introducing a new API. So there's this new class called android.os.trace. That's the API that we use internally in the framework to do all this instrumentation. But we're opening it up a little bit. There's this new API called begin section and end section. And here, this is an adapter. It's an adapter I created in a little test application. And at the beginning, I call begin section. I specify a string, so that's just the name of the section you're going to see in the profiler, so that name can be anything you want. At the end, you close the section by saying end section, and in the middle, we can have another section called bind. So you can nest the sections. The advantage of using this over trace view is that the overhead is almost non-existent. So it's not going to modify the behavior of your application when it's running, and the timings that it gives you are very, very, very precise. And if you do this, so if you use this new API, you have to use this other flag when you invoke systrace. You have to use -a, and you have to enter the name, the package name of your application. And
so we're not, to be clear, we're not recommending don't use traceview. Traceview is awesome. It is the tool to get all of the information on all the method calls that happen. However, if it's showing you timing about method call overhead at the Java layer, be suspicious, because there's a lot of overhead associated with the tool and with the instrumentation in particular. So if you want to eliminate that as a factor and you know the code path that you want to instrument very carefully, this is a really good way to get that information.
And very often the way we will use systrace, at least at our level, we will use systrace to get an idea of where the application is slow. And then when we have pinpointed that part of the application, then we'll go use systrace to see inside that block what is taking time. But this is much more efficient usually than going to traceview directly. So here I have two examples. Let's see, this one is, okay, the first one. So this is what a systrace file looks like. It is pretty scary, but it's actually really cool. So at the top here, you can see 3 CPUs. And if I zoom in, all
I like
the
the
way.
text heart better.
Yeah.
It was more romantic.
So if I zoom in all the way, and it might be hard to see, but you can see the name of the process that was scheduled on the CPU on CPU 0 at that time. So you can see, so if you're doing a lot of multi-threading in your application, it's a great way to see what exactly is going on. So maybe all your threads are running one after the other because you have a synchronization issue. You can see that in systrace. You can see the frequency of each CPU. So here, the CPU 0 and CPU 1 were running at full frequency. And you can see that sometimes they go back down a little bit. So I took this trace when I was scrolling. Don't remember. It was Gmail. And here at the bottom, I have the name of the application itself. So this is Gmail. And we can see what Gmail was doing. So here we can see one frame of the Gmail application. And we can see that Gmail took 28 milliseconds to render one frame. So that's too slow. But only less than 1 millisecond was spent on the Dalvik side executing Java code. So most of the time is spent executing the OpenGL commands. So that means that the app is not doing much at the Java level, but it gave us so many drawing commands that we cannot draw at 60 FPS. And if I keep zooming here, you can see all the individual OpenGL commands that we've executed for you. So if you work on games, that's probably a lot more useful than if you work on apps. But this is what a systrace looks like. And we should, I mean, there's a lot to say about systrace. We would need a couple hours, I think, to teach you exactly how it works. But go give it a try. It's really cool. Now, if you use that new API I just mentioned, the begin and end section, this is what it's going to look like. So here you can see the two tags I created. I know they're hard to read, but you see the strings create list item and bind image. I'm trying to zoom. Yeah. So again, you can see exactly how much time you were spending executing those sections. So here, I was spending 31 milliseconds in getView, and out of 30 milliseconds, 31 milliseconds, almost the entire time was spent binding an image. So I was probably loading the image from my getView method.
Tips and tricks.
Overdraw demo? Okay.
Yeah.
So we'll switch to code.
So I think, is this the one that you did your analysis for?
No, it's a different one.
Okay.
All right. So I have a very simple application that I'm going to install on this phone over there. And I'm using the new Android Studio, so hopefully it works. Yeah, it worked. So this app is just a demo app, right? So it's a list of images, and what I do is I fake loading the images from the network. So when I scroll really quickly, you can see a placeholder, and after a random amount of time, the image appears. So the scrolling is pretty good, but this is a Nexus 4, so performance is usually awesome on that device. Now, if we go in the settings, and we turn on the Overdraw debug, where is it? GPU Overdraw, here we go. So now everything becomes green and blue, and it's hard to read. But you can see that my application is mostly red. So the background of the app is blue, so that means there's something behind the background of the app, so we should get rid of that. The images are deep red, so there's clearly something else also behind them. And my 9 patches are green, so there's, again, something behind those things. So now we're going to go to the code and see what we can do to fix this application. So if we look at the layout of the activity, we'll look at the XML. How do I zoom? Here we go. Is the text big enough for everybody? Okay. You can see here I have a simple list view. That's all there is in my application. I have a list view, and I gave it a background because I wanted that custom color. But by default, on Android, when you create an application, you have a background already. It's the window background. It comes from the theme. So right now, I have two backgrounds. I have the one that comes from the theme and the one in my list. And we're going to draw both, and that's where most of the overdraw comes from. So instead of setting that background here on the list, what I could do is remove it from the list, then go to my style that was created for me when I created the application. And you can specify a window background. And here I'm just going to specify the color I was using in the list view. So now if I run the demo again, so you can see that it's not deep red anymore. We have this light red on the images, and the background of the app, it's a little hard to read on the screen perhaps, but it's white. It's not blue anymore. And the cards themselves, the 9 patches of the cards, not green anymore. It's blue. So we lost one layer of overdraw. But we can be even more efficient than that. So we have all those placeholder images that we show before we load a real image. And what's going on is once we're done loading an image from the network and binding it on the image view, we're not removing the placeholder. So the way to do this is, I lost my placeholder. Well, I don't remember how to do it in that demo, but you could just make sure that if you have placeholders and you put an image on top of it, make sure to remove the placeholder.
We're going to leave that as an exercise to the reader.
It's an exercise to the reader. Yes. Yes. Don't get ahead. Also, they can't hear you. And the last trick you can use, and a lot of applications can benefit from that. So this is the 9 patch I'm using for the cards. So this is this little, there was a little drop shadow, and there was this little white area under the image. So this is a perfectly regular 9 patch. There's nothing weird about it. But as you can see, like the entire inside of the 9 patch And let me show you the inside, show content. So the blue area here is where my images will go. So that area is a single opaque color, it's white. But because we're gonna hide it with an image, there's no reason for that to be drawn. So instead what you can use is you can modify your 9 patch, and it's a little hard to read on screen. Here you can see under my mouse cursor, there's a single transparent pixel. So I just cut a hole in the 9 patch, and this is the area that we stretch. So here again, the blue area on the right, you can see it's transparent. So we won't be drawing anything behind the images anymore. And the rendering pipeline is smart enough to recognize that there's a hole in the 9 patch. It will remove that part of the geometry and get rid of the overdraw.
Trilinear filtering is something we
4.2.
added, right, 4.2. So this API actually exists in a release that's out there right now. It's also referred to as MIP mapping, sort of classic traditional graphics technique of getting better image filtering when you're downscaling sort of extremely. If you're going down to more than half the size, it doesn't really matter that much. It's not going to change that. But the effect is, if you know that bilinear filtering is basically sampling the pixels on either side and top and bottom of the actual pixel that you're going to fill in, and then blending that result. Trilinear filtering is doing that same thing on the 2 images that bracket the image size that you actually need, and then filtering that result as well, and you get a much better scaling result. So for instance, I think we zoom in on these images, you can't really tell the difference there.
So this demo, yeah, go back. So in this demo, the 2 images were really large. They were bigger than the screen. And the same image was reduced twice on the left and on the right to less than half its size. On the left side, it was using the normal filtering mechanism, and on the right side, it's using trilinear filtering.
So if we zoom up so you can see the effect a little more clearly, you can see the one on the right is much smoother. We're not running into the same artifacts, the jaggy artifacts that we have on the left, because we're using more information about all of the map levels. So we can see was there the representation that MIP? Did I go past that one? Yeah, right. So if we look at this is what MIP mapping or trilinear filtering actually produces. Instead of just the one image that we're going to filter from, we actually produced powers of 2 sizes below that. And then we have all of those choices to then filter from when we do the MIP mapping. And there it is again, because it's so awesome. And here's the code. If you want to do it in code at runtime, set has MIP map to true, or you can do it in your XML drawable resource instead with the MIP map attribute.
Now we're going to talk a little bit about canvas layers. So this is the save layer API on the canvas class. So we have two types of layers. And if you don't write custom code, they don't really matter to you directly. But we'll see why they do matter even when you write an application using only views. So the first type of layer is what we call clipped layers. So when you call the save layer method on the canvas, you can pass a flag at the end, the last parameter. And here we pass the value clip to layer save flag. Then we draw stuff. So what this method does is very simple. So here we have our canvas. We invoke save layer. We're going to create an off-screen bitmap. So we're basically creating some. You can see that as a second canvas. And then when we draw the content, so here we're drawing an image, that image will be constrained to that new canvas. So it's not going to bleed out anywhere else, but we've created the second canvas. We have the second image in memory. This is very useful for a number of effects, especially opacity, and we're going to talk about that. Now, if you don't specify that flag, so if you call save layer and you pass 0 as the flag at the end, you're creating an unclip layer. And unclip layers are extremely expensive because when you invoke the save layer method, we still have to create that extra buffer in memory. But every time you draw something, what you're drawing is going to be drawn on every layer that the primitive you're drawing with intersects. So if you create n layers and the primitive you're drawing, your bitmap intersects all of them, we're going to execute the command n times. So that can be extremely expensive. So this is what we do in software. In hardware, we do it a little differently, but it's also extremely expensive. And I think we gave details maybe in one of our talks, I think maybe at Devox at the end of 2012, we explained exactly what happens in hardware. But the point is, if you're using save layer, be very careful. Because either in software or in hardware, the results can be pretty bad for your performance. And if you remember on Android, we used to have those fading edges in lists and scroll views all over the place. And that's how the fading edges are implemented. They use the save layer commands. So the top and bottom edges are one save layer each. And they were really expensive to run, and also they didn't fit the new ice cream sandwich theme, so we got rid of them.
Let's talk about alpha. So alpha is a cool property on view. You can make views translucent with alpha. It's very handy for fading views in and out. It's really so the general tip is use it, but be aware of what you're doing, and maybe there's a better way to actually get the effect that you're looking for. So there's lots of different ways to tie yourself in knots with alpha. You can set the alpha on a view in a couple of different ways. You can create an animation, object animator, or a view property animator that animate alpha over time, or you can use one of the old style alpha animations. These all end up doing the same thing under the hood, which is essentially creating an alpha layer, just like Romain already talked about. So we're going to create these intermediate buffers. We're going to draw stuff there. We're going to copy it back and composite it. A fair amount of work to go through, which is fine if that's what you need. But in a lot of situations, that's actually not what you need. You just didn't know that there were alternatives. So maybe it'd be good to find out what the alternatives are. It's also good to understand why you actually care about this. So you might think, well, you know, I've got this view and it's drawing several things. Why don't you just draw each one of these things with alpha directly into the screen, as opposed to creating this separate buffer over here, drawing everything and then compositing it back. So there's a handy little animation here to get you see what kind of effect you get. If you're just going to draw things with alpha directly to the screen, if we wanted to draw all of these images and then show a translucent view of the images, if we drew the images separately with alpha, this is what you get, which in graphics is called a mess. And what you actually wanted was something more like this. Right? We just wanted to fade everything when it was drawn together, not fade the individual items so that they all mush together into that mess. So what are some of the alternatives? So here's one. This is a simple one. We ran into this one in a notification panel, which won't be named.
It was Dr. Dan's fault.
It was Dr. Dan's fault, actually. The engineer that was playing with this was trying to achieve a particular effect, a specific color. It was basically a 70% translucent white value, right? Gave this nice gray, which is wonderful. Except what ended up happening was alpha was set on the text view, and the text view occupied most of a notification panel item, and there were several items on the screen, and you got a significant performance problem because of that. We were basically drawing most of the screen into these separate off-screen buffers and compositing back, all so that we could have gray text on the screen. The correct solution for that particular egregious performance problem was to use gray text. A slightly more direct or alternative way is if you really want alpha to achieve the exact color that you're going for, if you're animating the translucency of that text, you can set alpha directly on the text color itself, and we're going to draw that much more optimally than using the separate buffer approach. Image view, similarly, you can set the image alpha. This was new API in ICS. Android. Jelly Bean?
Yes.
OK. 4.1. You can set the image alpha, and then when we draw the image of that image view, we will use that alpha. Again, we're drawing directly into the destination buffer, as opposed to creating this set-aside buffer that we then composite from. Much faster if that's the effect that you're looking for. If you have a custom view, and you know that you're going to draw all these different operations, and you're happy to draw them translucently, then you can actually change the alpha on the paint and draw directly into the destination instead of setting the alpha directly on the view itself. Again, you know what your view is doing, so do the right thing for your situation. Don't depend on framework capabilities that are a bit more generic, but from which you might suffer because we can't know whether you're going to run into some of the artifacts that we talked about. Or you can set a layer. This is kind of a good thing to do in general, especially for animations. If it's a complex view and you want to fade the view, just set a hardware layer on the object during the animation, and then when you do an alpha fade on that, if you set the alpha property or animate the alpha property, then we can take care of that very fast. We create a texture map, and we just fade the alpha on that texture directly. And another related thing to mention is this new method that was introduced probably in API level 16, which is Haase overlapping rendering. We like method names that are really long, preferably if they actually go past the character wrap at the edge of the screen. This one didn't quite make it. This one we use under the hood to basically figure out whether we can draw optimally in this view. If there is no overlapping rendering in a view, we know that we can draw each rendering operation separately with alpha, and we'll take care of that very optimally. As opposed to, we don't know whether these rendering operations overlap or not, so we're just going to draw them all into the buffer and then composite them back. So if you have a custom view, you can consider overriding this method and telling us that you do not have overlapping rendering, and we're going to be able to handle alpha operations faster.
Okay, and we have only 5 minutes left, so we're going to start talking a little faster. Now let's talk about canvas. Here's an issue I see in a lot of applications, and I see a lot of confused people online asking about this behavior. So imagine you have a canvas, and that canvas is as 640 pixels wide, 400 pixels high, and you call canvas.getWidth and canvas.getHeight. So I see people who think it's going to give them the size of the window. I see people who think it's going to give them the size of the view, and the answer is both. So if we have this canvas in a window that's, let's say that you're on a Nexus 4 or a Nexus 7, and the window is about 1280 pixels by 800, and inside you have a view that's 600 by 300, and you call getWidth and getHeight. In hardware, you're going to get the size of the view as the answer. So you call canvas.getWidth, canvas.getHeight, and you're getting the size of the view. In software, you're going to get the size of the window. The point here is do not use the dimensions of the canvas as the dimensions of your view. You can just use view.getWidth and view.getHeight. There are really no reason why you should use the width and the height of the canvas pretty much ever. And you can think about it in a different way. If you were to rely on one of those two values to be exact, what would happen if instead of giving you the canvas of the window, we would give you the canvas of a bitmap because we're taking a screenshot or we're creating a drawing cache? Then you would get a completely arbitrary value. So be very careful if you're using those methods in your code. Now let's talk a little bit about clipping. I mentioned that we're introducing support for non-rectangular clipping. So if you're doing rotations and clipping, be very careful about the order of operations. So here, for instance, we're simply going to draw a rotated bitmap, and we want to clip that bitmap just in case. So we first clip with a rectangle, then we rotate by minus 30 degrees, then we draw the bitmap. So this is what's going to happen. You have your canvas, we apply the clip rect, then we rotate the canvas, we draw our bitmap, and this is our result. As you can see, the clip rect remained a rectangle throughout the drawing operations. So we can do it very efficiently. Now, if you do it the other way around, if you rotate first, then you use a clip rect, then you draw, here's what's going to happen. So we're going to rotate the canvas, we're going to apply the clip rect, we're going to draw, and the result is the same because we're not intersecting, we're not going outside of the boundaries of the clip rect. But now that we're back non-rotated, you can see that our rectangle is not a rectangle anymore. It's actually some sort of a diamond. So to apply this effect, what we have to do under the hood is we have to use something on the GPU called the stencil buffer. It's some sort of a mask. And we have to clear that mask. We have to render the rotated rectangle that represents the clip inside it. And then when we draw the bitmap, for each pixel, we have to test the pixel of the bitmap against the content of the stencil buffer. GPUs are very good at doing that kind of stuff. So if you do it once per frame, it's OK. But if you have a lot of very expensive drawing commands, or if you change the clip rect, or if you keep rotating in different ways, it's going to be extremely expensive. And again, remember that you can end up with a non-rectangular clip by just setting the rotation on the view if you do a 3D flip or just a rotation on the z-axis. Now, another source of confusion, so let's imagine we have a view that's 640 pixels wide by 400 pixels high, and we invalidate a small region of the view. So we call invalidate, we specify this little rectangle here inside, and we ask for the clip bounds on the canvas in the draw method. The clip bounds you're going to get are going to be different if you're hardware accelerated or if you're not. So with hardware acceleration, the clip bounds will always be the size of the view because we record a display list. So the clip bounds don't matter at record time. We just want to see all the drawing commands that you want to execute. When we're going to replay the display list, then we're going to apply the dirty bounds. In software, however, we're going to give you the exact clip bounds that you've set using invalidate.
We are not going to talk about reordering barriers. We will be posting these slides online. That is, in fact, the talk. There's some links to other information on related topics. Parlays.com has a lot of recorded talks that you can watch. And there was performance case studies you can check out online. Our blogs post all of this kind of information, or watch us on G+, where we also talk about this stuff. Thank you.